Welcome to Lecture 5, which is a continuation of our discussion of Boolean algebra. And the first problem I'd like to look at today is problem 2, this is in your book, 2.6a, which is, we're asked to write AB or C prime D prime as a product of sums. Right now it's in a sum of products form. You can see the plus sign indicates that we have a sum, and this is a sum of simple products of Boolean variables. So this is a sum of products form, similar to what we discussed in lecture 4, and we want to convert that to a product of sums form. And I'll show you one convenient way to do that. But before I do, I want to make an observation. The observation is just this very simple observation. If x is any Boolean variable and we complement it twice, we get back that same Boolean variable. To prove that that's true, we can make a truth table if you wish. So in this case, our function that we want to analyze is x complement complement. So we put the function that we want to analyze over here on the right. That's the way that truth tables will go, is that the function that we want to evaluate or analyze will go on the extreme right column, and all of the independent variables in the problem will go to the extreme left. And in this case, there's only one independent variable, and that's x. Then intermediate columns are used as intermediate points in the calculation. So in this case, there's only one independent variable, and that's x. There's no y or z or a or b or anything like that. There's only one independent Boolean variable, x, and so that's all we have over here in the leftmost column. And since it is a Boolean variable, it can have two values, 0 and 1. Now, perhaps some people don't even need the intermediate column of x complement. Perhaps they can see immediately what x complement complement is. But just in case you don't see that, I'll use this intermediate column of x complement. And of course, if x is 0, then x complement is 1. And if x is 1, then x complement is 0. And then if we complement those numbers one more time, well, the complement of 1 is 0, and the complement of 0 is 1. So sure enough, we can see that the column for x complement complement over here, the rightmost column, is identical to the leftmost column, which is the column for x. And this is true for every possible value for x, and therefore we can say that these two are the same. So in other words, we have verified here by the truth table that x complement complement is indeed equal to x itself. Now the reason that I made this observation is that one convenient way for converting a sum of products form into a product of sums form is to use the fact that the complement of the complement is the variable itself. So let me show you what I'm talking about. Okay, so we start off with AB or C prime D prime. Well, according to what we've just said, this is the same thing as AB or C prime D prime complement complement. That's just using the observation that we just made. Now, in order to simplify that expression, we're going to do the following. We'll write this as AB or C prime D prime complement. That term, as we've written it, just shows that we do one complement and then we do another complement, and we're just making that a little bit more explicit. Now, I'm going to leave that one complement on the outside of the brackets just as it is, so we'll still have brackets like this, and this complement here will come down. But for what's inside the brackets, I'm going to use De Morgan's theorem. Now remember, there are two forms to De Morgan's theorem. One says that the complement of a sum is the product of the individual complements, and the other one says the complement of a product is the sum of the individual products. Well, in this case, we're dealing with the complement. This dagger mark right here denotes the complement. So this is the complement of, and what we have in here in the interior is a sum. So the complement of a sum is equal to the product of the individual complements. So we have AB complement and then C prime D prime complement. This is how the everything that's inside the brackets will simplify. And once again now, notice that we have here, this is the complement of a sum is equal to the product. You can see that this is a product. If you wish, you can put the dot in there to emphasize that fact. This is a product of the complements of the individual terms. So here's the complement of the first term, AB, and this is the complement of the second term, C prime D prime. Okay. So this is how De Morgan's theorem could be used to make one simplification. Well, now it can be used once again, but this time we'll use the other form of De Morgan's theorem. Notice that each one of these terms that we have down here has the form of a complement of a product. And the other form of De Morgan's theorem says the complement of a product is the sum of the individual complements. So if we take this first one, it will give us A prime or B prime. Once again here, we're taking the complement of a product to get the sum of the complements of the individual terms. Okay? And we can do the second. We can do the same thing with the second bracketed term as well. So we'll get C complement complement, ORed with D complement complement. And then outside the brackets, we still have one more complement sign. Now, I don't think it will surprise you too much to see that we can simplify this a bit. We'll bring down the first term, A complement or B complement. But now C complement complement, just like X complement complement is equal to X, so is C complement complement equal to C. So this is C or D. And then we have this complement sign on the outside. Now we will multiply out everything we have on the inside of the brackets. So we get A prime C plus A prime, probably instead of prime should say complement, but you'll understand. I'll use those terms interchangeably. So A complement D, B complement C, or B complement D, and then we take the complement of all that. Now, notice that what we have on the inside of the brackets is a sum of products, and we want to take the complement of that sum of products. So here again is a chance for us to use De Morgan's theorem, where we say that the complement of a sum is the product of the individual complements. So we have A complement C. We need to take the complement of that, take the product of that with the complement of A complement D, and then we'll need B complement C, that needs to be complemented, and B complement D also needs to be complemented. And once again now, notice that this says that the complement of a sum, here we see that this is just a sum because these terms are connected by plus signs. So this is the complement of a sum is equal to the product, because these, we could, if you wish, put dots in between these. This is the product of the complements of the individual terms. So A prime C complement, A prime D complement, B prime C complement, and B prime D complement. And now, as our final step, we want to use De Morgan's theorem to simplify each one of those terms. And of course here we have, in each one of them, it is the complement of a product. Just like here we have the complement of the product A complement C. So the complement of a product, remember, is the sum of the individual complements. So we have A complement or C complement. Again, the complement of a product is the sum of the complements of the individual terms. So A complement, and C complement. And we do that for each one of these. A complement or D complement, B complement or C complement, and B complement or D complement. And then, as before, we will simplify all terms that have double complements, because A complement is A, B complement is B. So we have A or C complement, A or D complement, B or C complement, and B or D complement. And notice that now we do indeed have a product of sums form. You can see it's clearly a product, and each one of these is a sum, a simple sum of Boolean variables, and therefore this is a product of sums expression. And I claim that this is equivalent to this expression that we started with up here at the beginning, AB ORed with C complement, D complement. And now, just as practice, I would suggest that you try to go backwards and try to take this product of sums expression and write it as a sum of products expression. And of course that sum of products expression should be this right here. And so you should get A, B, or C complement, D complement. And I urge you to turn off the video now for a few moments and try to do that on your own, and then we'll all do it together. Okay, so I hope you had luck with that, and now we'll all do this together. I'll go ahead and end the first two terms together and the second two terms together, and then end all of it. So notice that if we end the first two terms together, we get, so this is a check. So and the first two together, we get AA, or A D prime, D complement, or A C complement. Notice there that I'm changing the order. C complement A is equal to A C complement, but we know that that's true because ANDing is commutative, or C complement D complement. And we get a very similar kind of thing with the second two terms. We get BB, or BD complement, or BC complement, or C complement D complement. Now, the way that we finish this all off very quickly is just to remember that any Boolean variable ANDed with itself is itself. So AA is equal to A, and similarly BB is equal to B. Now, I hope that at this point you see what we should do next. You should recognize that these three terms add to simply give A, and similarly these three terms add to simply give B. If you don't see why that's the case, I'll show you how it can be proven, but this is one of our simplification properties, and it's one that's particularly valuable to know about. But just in case you've forgotten how that goes, we'll notice that this could be written like as follows. We could rewrite this as A ANDed with 1, or AD complement, or AC complement, or C complement D complement. And similarly, the second term could be written as B ANDed with 1, or B ANDed with D complement, or B C complement, or C complement D complement. And now we can rewrite each one of those as A ANDed with 1, or D complement, or C complement, and then ORed with C complement D complement. And likewise, this could be rewritten as B ANDed with 1, or D complement, or C complement, ORed with C complement D complement. And remember that one ORed with anything, and it really is important. If this doesn't already jump out at you, it should be beginning to do so. One ORed with anything, you just need to know automatically. One ORed with anything is 1. And so therefore, this is equal to 1, and likewise, this is equal to 1. So these two terms now simplify quite a bit. We have A ANDed with 1, or C prime, or D prime, and B ANDed with 1, or C prime, D prime. And now another thing that should jump out at you is that anything ANDed with 1 is itself. So A ANDed with 1 is A, B ANDed with 1 is B. So we now have A, or C complement D complement, ANDed with B, or C complement D complement. And we're almost there now. Let's go ahead and multiply this out, and we will have A, B, or A, C complement D complement, or B, C complement D complement, or C complement D complement, C complement D complement, And probably some of you can do this more quickly, but I'll go ahead and spell out every step. So we have AB, or A, C complement, D complement, or B, C complement, D complement, or C complement, C complement, D complement, D complement. Remember, we can do that because ANDing is commutative, so we can change the order. And of course, this then gives us AB, or A, C complement, D complement, or B, C complement, D complement, or remember, any Boolean variable ANDed with itself is itself. So C complement ANDed with C complement is C complement, and D complement ANDed with D complement is D complement. And now, to finish this off, we could write that in this form: A, C complement, D complement, or B, C complement, D complement, or 1, C complement, D complement. And so that could be written as AB ORed with A, or B, or 1, C complement, D complement. And finally here then, once again, 1 ORed with anything is 1 itself. So this is AB, or 1 ANDed with C complement, D complement. And of course, 1 ANDed with anything is that thing itself. So we get AB, or C complement, D complement, just as we had up here at the very beginning. So that's the way to go from a sum of products form to a product of sums form, and then back from product of sums to sum of products. So that gives you a lot of practice with some of the simplification theorems, and also quite a bit of practice, which is important indeed, but quite a bit of practice with both forms of De Morgan's theorems, or De Morgan's laws, which once again we have two forms. The complement of a sum is the product of the individual complements. The complement of the product is the sum of the individual complements. You really need to have that memorized and ready to use. Next, let's look at problem 211A. We're asked to simplify an expression using just one of the theorems that we've learned. And in 211A, the expression that we're asked to simplify is the following. We have A complement or B complement or C ANDed with A complement or B complement or C complement. And if you look at that, I wouldn't be terribly surprised if your first idea would be to use De Morgan's theorem to try to simplify the second parenthetical term, because after all, that is the complement. This second term here is the complement of a sum, and so you might try to say that, well, the complement of a sum is the product of the individual complements, and that is correct, but that is not the fastest way to simplify this problem. The fastest way is to notice that this expression simply has one term ANDed with the complement of that term. And anything ANDed with its complement is 0. One ANDed with one complement is the same thing as 1 ended with 0, which is 0, and 0 ended with 0 complement is the same thing as 0 ended with 1, and 0 ended with 1 is also 0. So anything ended with its complement is always 0, and therefore we can do 211A extremely easily. Let's look at perhaps 211C as another example. So in this case, we have AB or C complement or D ended with AB complement. Now, I will admit to you that I have not memorized every single one of these theorems. I try to be familiar with them, but after all, it is difficult perhaps to memorize all the theorems you have in every single class. But as I say, you just want to have some familiarity. And certainly, it catches my eye here that we have AB at first, and then we have AB complement here. We're here in the second term. So if I were you and I were faced with a problem like this, what I would do is I would let AB, I would simplify it and call it X. And similarly, I would call C prime or D Y. And of course, AB again is X, but this time we have that complemented, so we have X complement. So this has the same form as X or with X complement Y. And okay, I admit I have to take a break on that one because this one is a little tricky. If you want to know immediately what form this is, or perhaps let's just say which simplification theorem, you need to simply look at I'll say C2-14D on page 42 of your text. And that is the theorem that is appropriate in this case. But I will show you how we can get to the desired result. And it would be as follows. We know from our previous work that X or XY is the same thing as X. Now, how do we know this? Well, X or XY is the same thing as X ended with 1 or X ended with Y, which is the same thing as X ended with 1 or Y, which is the same thing as X ended with 1, which is X. So now it might seem a little counterintuitive to take that first X and to rewrite it as X or Y, but it will lead to a simplification. So that's why we would do that. So instead of writing X or X complement Y, we will write X or XY or X complement Y. And I want to make sure over here that you understand that maybe I'll go ahead and just I'll put a box around this part because we have not simplified that. Down in this with this work below is just a elaboration on a way that we can rewrite X. Okay, so coming over here, we bring the x or x complement y over here, and then we use the work we've done over here on the left to rewrite x as x or xy, and then we just bring the x complement y over to the right. And now I believe you can see why we want to do that, because we can now associate the xy and x complement y together, and we get x or x complement y, and of course x ORed with x complement is 1, and 1 ORed with anything is that thing itself, so therefore we simply have x or y. And to finish up this problem then, if we recall what x and y are equal to, we have then AB, that's x, and y is C prime or D. So we conclude with AB or C prime or D ended with AB complement is simply the same as AB or C complement or D. Now, I'll certainly admit that it was a little tricky to find that one. Unless you know the correct simplification theorem, it would be easy to miss that one. But again, don't worry about this, because we are about to learn some simplification techniques that will make all of this automatic. And actually, I think that this is a good chance for us to look once again at a truth table. So now that we've obtained that result, let's just backtrack for just a moment, and let's go ahead and look at this theorem that we just used, or that we just quoted. We didn't actually use it. We went ahead and showed the steps, but if we had wanted to use the theorem, we could have. And so let's look at the theorem for a moment. So 214D on page 42 says the following. It says xy or, xy complement or y is equal to x or y. And so let's see how we might use truth tables to prove this. Well, remember, in the truth table technique, we will write the independent variables on the left and the dependent variables, or the function, actually on the right. So in both cases, whether we're looking at the left-hand side of this equation or the right-hand side of this equation, in both cases the independent variables are x and y. So I'll make one truth table with x, y, and then let's say xy complement and xy complement or y. You can see that the term on the extreme right is the function, is one of the functions that I'm interested in. It's the left-hand side of the equation. The two columns on the left are the independent variables, and I've used one intermediate column to help me calculate, to help me do my calculations. So now we have two independent Boolean variables. We have four possible combinations: 0, 0, 0, 1, 1, 0, and 1, 1. Now for each one of these cases, we now need to calculate x ended with y complement. Well, we can do this pretty quickly in the following way. Whenever x is, in the first two rows, x is 0, and 0 ended with anything is 0. So it doesn't matter what y complement is, these first two rows will give us 0 because x is 0. Now, in the final two rows, x is equal to 1, and so xy complement is the same as 1 ended with y complement, and 1 ended with anything is that thing itself. So in the last two rows we get y complement. Well, in this row y is 0, and the complement of 0 is 1, and in the last row y is 1, and the complement of 1 is 0. So that is the value of xy complement for each row. And now we finally are ready to calculate the left-hand side of the equation in every possible case. And we do that by simply ORing the second column of this table with the third column. So 0 ORed with 0 is 0, 1 ORed with 0 is 1, 0 ORed with 1 is 1, and 1 ORed with 0 is 1. So the left-hand side of that equation is always equal to 1, except when x and y are both 0, and in that case is equal to 0. Now, let's do a truth table for the right-hand side of the equation and see what it looks like. Now, this one is a little bit simpler. Again, we write our independent variables on the left, and we write the function we're interested in on the right. And in this case, I didn't use any intermediate columns at all because this one's so simple. Once again, we have two independent variables. So we have four possibilities: 0, 0, 0, 1, 1, 0, and 1, 1. And now if we OR those two columns together, 0 ORed with 0 is 0, 0 ORed with 1 is 1, 1 ORed with 0 is 1, 1 ORed with 1 is 1. And now, if you compare this column and this column, you see that for every possible combination of x and y, it is indeed true that the left-hand side of this equation is equal to the right-hand side, and therefore xy complement ORed with y is indeed the same as x ORed with y. So this, we have proven the simplification theorem in this particular simplification theorem in that way. I'd like to do now one final problem for this lecture, and that is problem 213 B. In this problem, we're given a circuit that looks like the following. So we have an input A, and an inverter, an AND gate. The output of the AND gate goes to an OR gate. The output of that goes to another OR gate. And the output of that will be called F1. And we have another input B, with which we do the following. Okay, so that's our circuit. And actually I see that I've made an error here. This is the circuit not for problem 213b, but for problem 213a, which will be fine. So here's our circuit for problem 213a, and the instructions in your book tell the following. It says, for this circuit, find the output, and then we want to design a simpler circuit that will have the same output. So let's see how this will go. Well, we'll start up here with the A input. We know that the input A will be coming along this line for the second input of this AND gate. And for the top input of the AND gate, our analysis goes as follows. We have A coming into this inverter, but then when that gets inverted, we have a complement. So here we have A and A complement going into this AND gate, and we know that any variable complemented with its, any Boolean variable ANDed with its complement will give 0. So the output of that AND gate will always be 0 regardless of the value of A. Now once we see that, that makes the rest of this problem very easy, because we see that the second input to this OR gate will be B, and B ORed with 0 will give us B as the first input of the final OR gate. Now if we look at the second line, we have a B here and B. Any Boolean variable ORed with itself is itself, so we have B here, and the same principle arises again. Any Boolean variable ORed with itself is itself, and so we have B, and therefore F1 is simply equal to B, and therefore if we want a simpler circuit, it would simply be the following, because F1 is equal to B, so that we don't need any components at all except for just a wire, which will make F1 always exactly equal to B. So that's how we would do a problem of that type. Let's now discuss the problems for this lecture. Problem 5.1, which of the following expressions is equal to 0 for all possible combinations of x, y, and z, except when x is equal to 0 and y is equal to 1 and z is equal to 0 simultaneously? In other words, all three of those statements have to be true. X must be equal to 0, and y must be equal to 1, and z equals 0. If those three conditions occur simultaneously, if all three of them are true, then the expression we're looking for is equal to 1. But in all other combinations of x, y, and z, the expression we're looking for must be 0. So I'll just give you a little hint on this one. Since we have 3 Boolean variables here, we have 2 to the third power, or 8 possible combinations of x, y, and z. We could have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So we have 8 possible combinations. In all of those combinations, the expression we're looking for is equal to 0, except the combination x equals 0, y equals 1, and z equals 0. So which of the four expressions given here, A, B, C, and D, which expression satisfies those conditions? That's problem 5.1. And then in problem 5.2, we have a simple circuit, and you're supposed to find the output. Either A or B or C or D represents the output of this circuit. You determine which one is correct. And that concludes lecture 5.